location with very few other sizes on Flora Bank. So it's a very reasonable curve to use this. And to move Flora Bank sand, we need 23 centimeters a second of current. And I'd like you to remember, 23. That's what we, as soon as we get to 23 centimeters a second of current, we can move that sand. And in fact, and once it's moving, this part, it can stay moving until we actually reach 3 centimeters a second. So once you get the sand moving, it can keep moving under much lower currents until it drops to 3 centimeters a second, I think it is. Now, Petronas, in their English, in the latest report, claim that the grain size is fine sand, which is right here. Now, fine sand, I can only imagine that they're describing it as fine sand because that implies less energy. If the finer the sediment is, in conventional thinking, the finer the sediment is, the less energy is present to have deposited that kind of sediment. So they've told us that it's not medium sand, and they have the grain size data, so why they would call it fine sand is beyond me. I don't understand it, but it's very important that they've done that. But they put the threshold of movement at 35 centimeters a second, between 30 and 40 centimeters a second, which in fact can move sediment as coarse as over a millimeter. So they've exaggerated the amount of movement that's required to actually move the sediment, and they've de-exaggerated the size of the sand that's there. And why, I can only imagine, is to get your mindset into the fact that the currents must be quite low. And here is an illustration of what this means. This is the model tidal current at a particular location on Flora Bank, and this is at another location on Flora Bank. So this is over about 2 months, 3 months, I believe, 900 hours. So you can see that these are tidally driven currents going through time. And what they've done is they've put this brown bar or orangey bar at 30 to 40 centimeters a second, 0.3 to 0.4 meters per second, as the threshold of motion of the particles. And you can see that where these velocities peak above the threshold is the only time you can move the sand. And not much sand is going to move if these predicted currents are correct. At this location, you can see just the peaks picking up above the threshold of motion. And therefore, if you look at those curves, you will come to the conclusion that most of the currents at Flora Bank won't move. But if you put the bar where it should be, in my blue bars here, between 20 and 30 centimeters a second, you'll see now that we have a whole lot of the curve above the threshold velocity. And I don't believe the currents, these model currents anyway. I think the model currents are actually higher than what is being shown here. But even if if we were to accept their data, we cannot accept the threshold of velocity of movement. All right, I'm going to just show you the averages that I got in the kinds of currents that we have. This is a very simple plot of the velocities based on all the currents that I got at early flood tide, and then mid tide, late flood, very late flood, just all put together, just to look at the average velocities we get at the different phases of the tide. And we can see that my red line is the threshold velocity of 23 centimeters a second. That's that at Very early flood, we're below threshold. As soon as we get to mid-flood, we're above threshold, late flood, very late flood, and then at high water slack, we're still got a very strong flood tide, flood current, which shows you the asymmetry of the currents, and the asymmetry of the currents is probably very, very, very important in the consideration of how the sediments are behaving on Flora Bank. Then, when we hit very early ebb, we drop the current down. It's still slightly below threshold velocity, and then mid-ebb, it's on the ebb currents, mid-ebb and late ebb, that we have the highest velocities of all on Flora Bank. And then very late flood, it drops, and by low water slack, we're below the threshold of velocity. There's a few niceties about this curve, which I'll probably allude to shortly. Am I all right for time? I'll just be a few more minutes. So, in conclusions of this, then, the latest Petronas submission minimizes the current velocities on Flora Bank by, first of all, claiming the bank is composed of fine sand when it is medium sand, and two, using unrealistically high threshold velocities to initiate particle transport. By incorporating this false information, Petronas is able to conclude that the sand on Flora Bank cannot be moved most of the time. And therefore, a reduction in process energy impinging the bank caused by the trestle jetty and the ships will have no effect on its present apparent stability. Both DFO and NRCan share a concern that Petronas has underestimated the current velocities on Flora Bank, but their recommendation that further current data be obtained has been ignored. Instead, Petronas has included a previously unused ADCP transect that demonstrates higher velocities than predicted do exist, but claims there is no reason to change earlier conclusions based in the numerical model. Now, what they've written is sometimes ambiguous. I mean, NRCan's stuff is very, very difficult to. First of all, everyone seems to agree on the results of the STA. Agree on the results, not the prediction necessarily. But NRCan states that the prediction that I made, the Great Escape prediction, is hypothetical. Now, you can't agree with the STA and then say my prediction's hypothetical. That's impossible. It's a reasoned, defensible prediction made on the basis of how everyone is agreeing Flora Bank must be working. On the basis of the tidal current data collected for this study, it is clear that current velocities are consistently over threshold across the entire bank and at nearly all stages of a spring tide. I just want to show you the average currents at each route, because this actually really is a nail in the coffin, I think. But in route 1, the average current in the whole of route 1 at all stages of the tide is 20 centimeters a second. At route 2, it's 28 centimeters a second. It's higher on the Inverness side. In the middle, the average current for all stages of the tide was 37 centimeters a second, and at route 4, 33 centimeters a second. So there's some very important features about those numbers. One is that the currents are stronger on Flora Bank itself than at the edges. That is exactly in keeping with the STA theory, that we have to have stronger currents to keep that sand as coarse and as well sorted as we've got. It's impossible to have them reduce. Secondly, what did I do? Oh, I didn't. Sorry. Secondly, the probable reason for having higher currents on this side is because of the influence of the Skeena River and all the currents that are coming in. And so when the Skeena River is flowing, the ebb currents the ebb currents on Flora Bank are enhanced, they're increased. And if you, the body of water between the island and is it Smith Island, right? Is it? Yeah.
No, it is.
Smith Island, yeah. And Flora Bank is not very wide, so that we cannot build very much waves on this side of the bank, and we have higher currents. On this side of the bank, we've got less currents, and that allows the bank to be divided into two halves. We have the southeast half, which is dominated by sand waves formed by the ebb currents coming out of Inverness Passage. And you see these sand waves are all smooth and well formed, and as the ebb comes out and spills over, we've got sand waves that have progressed across the bank all the way to here. On this side of the bank, we've got sand wave fields modified by westerly waves. You see, these are jumbled, and they've been altered by the wave regime on this side because it's facing Chatham Sound. So we know that we've got more tidal currents on this side, less on this side. How do we keep the two walls of energy equal? Because we have the waves on this side. So the waves and the tidal currents together have to keep the wall of energy the same as this side. And that's why I can say that the velocity differences between the northwest and southeast halves of the bank emphasize the importance of waves on the northwest side to prevent the loss of sand from Flora Bank. Because the model fails to explain the present sedimentology or morphology of Flora Bank, a no-harm prediction should not and cannot be accepted. And finally, when I go back to the Great Escape concept, I can conclude that the loss of energy, particularly wave energy, caused by the structure remains unavoidable. And given that the tidal currents can and do move the sand on Flora Bank. We can't see the very bottom of this. Well, I knew there was a breaking of the sentence, but hang on. I've got to get my thunder right here. So the tidal currents can and do move the sand on Flora Bank, and so the Great Escape remains a defensible prediction. Thank you very much.
Thank you. Any questions?